everyone. We're going to try to make a slow start, so John is going to come back in a second and he will explain why he is integral to today's event. First of all, welcome back to everyone who has been here before. I see quite a few familiar faces, which is lovely, and I know a few of you online are rejoining us today as well, which is awesome. So today we're going to be talking about the hidden dangers of AI, and we have our lovely two guest speakers here today. Obviously, they're going to be telling you everything about their topics later on. I'm just going to quickly go through some of the house cleaning and some of the additional information. So as every time, here's some information for the people online. Our talk will roughly last 50 minutes. So we have two speakers. Each of them will roughly talk for 25 minutes, and then we do the Q&A at the end. We'll also try to answer all the, the online questions. I will try to sit at the web and try to answer everything. And everything we don't get through today, I will pass on to the speakers afterwards and might ask them if they could quickly send through some answers whenever they're free to do so. We will most likely not get through all the questions, but we'll try our best. And everyone in the room, your questions, you can just kind of pounce on them after the talk and ask any additional questions you might have, I say with a big smile at the speakers. Just a quick reminder, and I've gotten a lot of emails about this. So this is a speaker series of altogether 6 events. And if you attend online or offline, more than 3 of these talks, you can get a certificate. But for that, for us to know that you attended more than 3 of these events, we need you to scan the QR code and give us at least your details, so your name and your email address, so we know you have been here. And then you will get the certificate after the whole speaker series is over. So the last event is in April next year. And then you need to give us some time to process all the information. And so in May, we'll send out the certificates. I will show the same QR code a few more times throughout the presentation today. But if anyone has issues, I'll quickly wait because a lot of phones came out all of a sudden. So I'll try to make sure that everyone has the time they need to do this. So again, as a reminder, we need you to register just so we know you're actually here. I recognize some of the faces, but we want to try to be as fair to everyone as possible. Okay, there's still one phone on the loose. Okay, I think we're through, but it will reappear. If anyone has problems with this QR code, or you can ask me at the end, I can bring it back up. So just a quick reminder, we did send out a privacy notice, and these crazy people is not Dawn. Dawn is lovely. She's in the back in a very bright pink jumper, really nice, you can spot her easily. So we will be taking pictures today, and if there's anyone who kind of thinks, nah, not for me, please just let her know. It's more for us to kind of showcase how good these events are, to attract more people to come over and have a bit of evidence that we're doing an okay job. I would pass over to John right now. And then he can introduce or pass over to the guest speakers afterwards.
Oh, I'm passing over to the guest speaker, right?
Yes.
Do I have a...
Yeah, yes.
Oh, crikey. I normally just shout at these things. So welcome everybody, welcome to the Institute for Safe Autonomy. As the name implies, and those of you that are going on a tour later, I will tell you more, but we are all about looking at safe, reliable, trustworthy, robotic and autonomous systems. So obviously the subject of today's seminar and webinar is particularly relevant and pertinent. So all I'm here to do is just to give you some general housekeeping and just to say welcome to those of you online. I know you're at distance and you can't fully experience the wonders of this building, but you are more than welcome at any time to come and visit us. Just drop us a line at isa@york.co.uk. So general housekeeping, there are no fire alarms expected today. If the fire alarm does sound, I will be at this room instantaneously or nearby. But basically, go out the way you came in, and the fire assembly points are at the rear of the building and at the front of the building just before the piazza, okay? But as I say, we're not expecting any fire alarms, and one of us will be here to make sure that everybody is safely out of the room. Toilets on this floor, if you go out of either door, turn to your right to the end of the corridor, turn to your left, and the toilets are on your left-hand side, and there are many of them, and they are unisex, just for reference. And for those of you that are online, if for whatever reason your connection does drop out, just reconnect with the same link that you used previously, but hopefully there shouldn't be any connectivity issues. So without further ado, and for those of you that are going to have a tour, that will be with myself and Dr. James Hilder, who's our technical manager, and we'll reappear around about 3:15, 3:30 for those of you that are wanting a full tour of the building, and we'll show you all of our labs, test facilities, etc. So without further ado, if I could hand over to our first speaker, which is Dimitar. Yes. So,
Thank you very much.
Thank you.
I'll get that mic on. I'm assuming it's already switched on. And I'll do my best to clip it on. Okay. So. Okay, so, well, thank you for inviting me to give that brief talk. And let me see if I can get my slide there. Oh, that's me. Okay, so what I want to talk about is AI and bias. So the first general title that you saw, The Hidden Dangers of AI. That's an accurate title. It would be equally as accurate as The Hidden Dangers of Antibiotics. Some of us are allergic to certain antibiotics, so you don't want to take them. But we still think Alexander Fleming did a great job. And in that vein, I want to talk a little bit about simply how AI should be managed and developed safely. So I'm a member of the Artificial Intelligence Group, Computer Science Department, just to give a bit of background. And for those of you who are not physically here, here is a nice view that you can see if you just pop outside. So it's a nice campus. Why not show it? So the outline of what I want to say is very simple. I want to say what AI can do at a certain level of abstraction, what it should do, and we'll also talk a little bit about what AI may actually do and how expectations and reality may not exactly meet each other on all occasions. So first of all, a couple of abbreviations, perhaps. Artificial intelligence. Machine learning is this subset of artificial intelligence which is probably most directly involved in most of the applications that you've seen so far. So basically, when you develop a system that is trained on some data. And first of all, we should say, okay, so if I'm going to learn from data in the same way as in medicine, you have, what do they call them? Observation-based approaches, experience-based, I can't remember exactly. But basically, it's a data-driven approach. You shouldn't just say, I know that's how it is, but you want to back it up with facts. So we need to have some databases. And of course, when we have the data to learn from, if the information that is supposed to be relevant to our decisions is not in the data, well, we're not going to be able to learn anything, right? Or at least we're not going to learn the best possible behavior or decision algorithm, whatever the application is. So first of all, we need to consider what we may call a language bias in the context of machine learning. So what is the language that I use to describe my data? And if we need to make sure that the data contains as much relevant information as possible. Of course, it's also the case that we don't want to have any data that is irrelevant, but it's in most cases we don't exactly know what part of the data is relevant, what features are relevant and what aren't. And sometimes it's the subtle combinations of features that give us the necessary information. So for instance, if a doctor speaks of syndromes, this is a combination of symptoms. So you have individual features that you can observe in the patient, whether they have fever or not, whether they have a rash, and so on. When combined together, that results in a syndrome, which is a kind of higher level feature that you can then use to make a decision. So we also, the way in which the data is represented can vary. A lot of the time we think computers, therefore numbers. Yes, but a lot of the time the number actually is not a genuine thing where we can subtract two numbers and get a distance between two observations. They can simply express some sort of ordering. I'd rather have this than that, but not necessarily a distance. I mean, if I have to make a marriage proposal, I can say this is my top choice, but it would be totally irrelevant and probably silly to say, and my second best choice is that far from there. at least not out loud. Depending on the data type, we also have different approaches, and what the approaches can capture varies with the data. This is just a simple example of, you have to have the feature in order to be able to learn something based on this feature. And, what we learn could be something very simple. We could simply say, I only like cars that are large and blue. So the language that we use to express our model, our hypothesis about what is it that we're trying to capture, can vary. It could be something explicit that can be inspected, observed, and actually approved by a human, or edited even. Or it could be something a lot more obscure. So in some of the most popular approaches nowadays to machine learning, and therefore to AI, are based on the so-called deep learning methods, where essentially you have a massive set of functions, if you want, or of elements that add up their inputs. They modify them using some sort of function. Say, I add up all the inputs and I use them as the input of a tangent function or something like that. And then the output is then provided as an input to the next layer, and so on. So you have systems that have billions of such components. The result is still the same kind of output. If you're trying to classify observations, you can say, is this a cat or a dog, or something I haven't seen before. But what underlies that process can be so complex that it's impossible to immediately observe and discuss whether that system is adequate, or whether it's the features that it uses are appropriate, either to its goal or in terms of some of the ethical and legal norms that we want to comply with. So my talk was called AI and bias. So another meaning of the word bias is when we try to model the user and, for instance, decide what is the best action or what is the best thing to offer to this person to buy, they may not be able to rank their, as I said, their preference. They may not be able to assign a number to their choices, but they may still be able to say, okay, if I have to choose between these two cars, I'll buy this one. So that's a clear preference. And based on that very simple information, you can build a model that decides what is it that you actually like. And that could be a way of gathering information and then building a model out of this. So this kind of information, in this context, bias is nothing bad. I mean, you simply say, this is what the human that I'm trying to model, or whose decisions I'm trying to anticipate, this is how they reason, this is what they want. And when we build a model that is trying to explain the data that we're looking at, we also can choose to approach things differently. We can say, I'm going to build the simplest possible model that fits my data. Or you may say, I'm going to build something very, very detailed, almost like sticking to the individual examples and not trying to generalize too much. And this choice, I mean, at either end of this kind of axis, you can make arguments for and against. I mean, a lot of the time we say, oh, there are some clear-cut philosophical arguments for simplicity. And we all probably have heard of the Occam's razor, although what he wrote in the 11th century in Latin is probably not exactly what we now claim to have for him to have said. But still, there is a preference for simpler explanations that draw on fewer observations, on fewer features of what we observe, and so on. There is no scientific argument, even if we just look at the accuracy of these models that we get, that a simpler model is a better one. But of course, a simpler model is easier to inspect and easier to judge in terms of safety, in terms of benefits, and so on. So this is something that the designer of the AI system will also have in mind. And whatever they put in the system will do. So the system will produce results that we may judge somehow suboptimal. But it's still based on the design decisions that are made also at this stage. Sometimes when we search for an explanation, when we search for a model that tells us what to do in the future in similar situations, we may not be able to inspect all the possible alternatives. And in this case, there may be a strategy that is implicitly embedded in the system that says, well, start from this end of the range of possible models and stop with the first model that is good enough. And again, that could implement a bias towards simpler explanations. If you say, well, I'll look at the color of the car that this chap wants to buy, and if it turns out he only likes blue cars, well, I'll sell him a blue car. But if there are blue cars that he doesn't like, I'll also look at the model, the car size, and so on. So I'll extend the model and make it more complex. But it doesn't mean that's the only approach. You can say, well, the guy comes and says, I had a Toyota Corolla, whatever, make and model. And then you say, well, he probably wants exactly the same. And then you can say, well, would you be willing to consider something very similar but not the same? And you can start relaxing these constraints. So you start from the most specific kind of model to something that is more general. And this may not be a bad approach when you implement medical systems where you know what to do in a specific case, but you don't want to overgeneralize because your therapy, for instance, your treatment may not be suitable to a patient, to a situation that is very different. So you don't want to be too gung-ho about this. And essentially, if you have a set of possible features, I don't know, large, small, even if they're binary, cheap, expensive, and so on, the possible combinations of these features is basically an exponential, a number that grows with exponentially with the number of features. And if you want to consider in how many ways you can split these two sets into good choices and bad choices, that actually grows exponentially. That's what I wanted to say. And then the system, a system that is trying to learn what you like, what you dislike, for instance, it will have less work to do if you already restricted some of these choices, some of these possible splits. So you have fewer theories, fewer models to eliminate. But then if the right answer is excluded already at this step, then you're never going to get the right answer. So there is this trade-off between speed and accuracy. And apparently Frank Lloyd Wright, the architect, said once, an expert is somebody who doesn't think, he knows. So in that sense, if your experience has narrowed down the number of choices to literally to one, because for what I see, that is the only way to do it, to me that probably implies some narrow-mindedness that is definitely not present in his work. But you can see the idea that with experience, you also narrow down the number of choices that you consider. A chess player wouldn't even consider the majority of possible moves because they are obviously not relevant. So now I said in a few words what AI can do and cannot do depending on how we implement it. What we should do is, there are some legal aspects of it. We shouldn't discriminate on the basis of something that is known as protected characteristics in law. And here is a list of protected characteristics as defined in UK law, I guess, in the law in England and Wales. So if you make a decision based on these characteristics, that could mean that decision is basically unacceptable and not in compliance with the law. And a few of you probably at least remember that some time ago, about 10 years ago, the European Union outlawed the different pricing of car insurance based on the driver's gender. And here's the news from 2012. Well, that's what the news was. That meant that women, in particular, had to pay more because apparently, if you actually looked and you used this as a salient feature in your decision process, it said, well, women are better drivers. They don't claim, for accidents that often, or they claim less. Nevertheless, that was decided that it's not acceptable, and therefore went out of the window. So it doesn't mean that the system wouldn't have done better using that feature, but it was considered unacceptable from that legal point of view. There are some strong recommendations, not the law. For instance, that when you make a decision, the selection ratio of, say, if you appoint people from a minority group should be at least 80% of the percentage of people you select from the remaining majority group, or on average for the whole population. I'm not sure actually, but what this says is you separate them into minority and the rest, and that difference shouldn't be more than 20%. And in AI, a system can actually show preferences that it shouldn't show, depending on several reasons. You may have a historical bias. Your data may suggest that something is the case which is no longer the case, so you shouldn't be looking at data that is outdated. There may be a bias that is related to, I'll give you another example. Let's say you want to say, okay, I stop and search people whether they have, I don't know, knives on them or drugs. And my initial sample may show that a particular minority group is more likely to actually be committing an offense by doing one of these things. So if you start stopping them even more, of course there will be an even greater number of observations where, yes, they will be committing that offense. At some point you may even stop looking at the rest of the population, because that sampling has yielded so much seemingly positive results. Of course you don't want to do that. And so when you obtain your data should represent fairly your entire population. And that is something, again, to be considered, because, again, if you don't have observations about part of the population, how can you decide whether you should take a particular action? And now when we go into actually using some of the AI systems that we've been all playing with in the last few months, you say, okay, give me a picture what a typical pilot of a passenger jet looks like. And these are some of the images that I get in return. So you may say, okay, do I get more men? Do I get more women in this sample? And what is the age, for instance? And as it happens, in the top 5 pictures, women look a lot younger than the men represented there. The question is, why? Is that the case? I mean, would that woman retire in 5 years, so she would never appear as a 50-year-old woman in a picture? Which in this case obviously is generated by an algorithm. Further down, if we follow these examples, if I ask DALL-E for images of a primary school teacher, you'll see that in this picture there are 3 women out of the 4, and they're all women of color. Okay, now if I say, how about a primary school head teacher? And all of a sudden, there is nobody with a dark skin in the top 4 images. So clearly, the system is the representation of, or the understanding of what this job involves, or what people doing this in this profession look like, is biased. But the question is why? Is it because the data that the system has been trained on has been biased? And if that's the case, how can we correct for this? And I mean, the answer is obvious. Again, we want all the parts of society to be fairly represented in our data. Even if this means that their representation in the sample is not going to be proportional to their representation in the current population, because we want to put the wrong things right. We want to rebalance some of these, how these minorities are represented in a particular profession or in a particular situation. What I'm saying here is that my data that I provide can also have some inherent ambiguities. So the data, if the data is not labeled, because a lot of the time for our system to work correctly, we want not just to have observations, but to have some labels that are provided by a human, an expert, if you want. So in the case of text, where you want to train your AI to understand what is being said, some of the systems require input where you actually say things like, okay, if I say I walk to the hotel by the river, what does it mean? Is this a building that is by the river, or did you just walk by the river to get to that hotel, which might not necessarily be by the river? And sometimes there is no straight answer. There is no single answer. So there may be some ambiguity. And if your AI system is forced to make a decision rather than say, well, it could be either, then again you're going to get some arbitrary output, which is not going to necessarily be what I expect. So what I just said just a moment ago is that if most of the people that a given institution has been appointing are white men, you may say, well, clearly a white man is a safe bet. But then you say, well, that doesn't mean that it should stay that way, because maybe, not maybe, but absolutely by all means that there will be also women, and there will be people who are not necessarily white who can do the job. But if your data only contains these examples, or is strongly biased towards these examples, then the result may be biased as well, and that means you want to sample your data set from the different populations in order to represent them fairly in what is being done. So I'm running a little bit out of time here, but I just wanted to mention one work with one of my PhD students, Charmaine Barker, where imagine you apply for a job and somebody looks and says, oh gosh, the vocabulary of that person shows they went to a particular type of school, they come from a particular part of the country, or they come from a different country, and you may decide on the basis of this. So how can we remove the potential for this kind of injustice, if you want? What we did was, I'm just going to quickly skip, we took, in this case, some comments about whether you liked a holiday resort or not, and we used one of those AI tools, ChatGPT, to rephrase the text so that rather than showing some language peculiarities like America, showing that the text was written by an American or by a British person or by an Australian person, the result, the text became more kind of neutral with respect to the vernacular that was used. And as a result, when we try to train a system, again an AI system, that guesses whether you are from Britain or from the US or from Australia, the system was much better at the original text compared to when it saw the same text with the same content, but in a more neutral language. And we tested actually whether the meaning has been preserved, because we were looking at comments, whether they're positive or negative. The amount of positive comments remained the same, statistically speaking, while it was a lot harder to guess where you come from. And if this is on a job application, that removes the chance that you're going to say, oh, he's from this part of the world, so I probably wouldn't consider him or her. And this is pretty much all I wanted to say. Thank you very much.
So I'm Steve Tait. So I'm here to provide a case study around AI. So I've been working in this field probably for the best part of the last 10 years. So my background really is I've worked with starting as a small SME. We worked in the technology space, in the rail technology space, and then we built a lot of systems around vision, and obviously within the last 10 years we've seen a revolution in AI, and we jumped on that bandwagon, I'm not ashamed to say. So I'll talk a little bit about those experiences. I'll provide a specific case study from the industry I work in, and I'll give it more of a business viewpoint rather than the technology viewpoint. And I'll hopefully provide a few learnings from our experiences as well. So AI in rail then. So AI in rail is everywhere at the moment, it's fair to say. So everything, it's a global phenomenon really, and I think what you see is the rail industry, like others, is a very traditional industry which is trying its best at this point to automate. It's trying to struggle with costs and reducing costs, and is struggling with availability of people, engineers, and it is primed for automation at this point. And you see it across all parts of the rail sector. You see it across everything from monitoring revenue, so are people entering onto trains without tickets, all the way through to autonomous driving, autonomous signalling, and how we maintain infrastructure as well. The difference really is that the rail industry is a very slow to adopt place. AI, when just watching it and observing it, is very fast paced. 2 years ago, we started to get our heads around things like TensorFlow. We start to embed that sort of thing, and then all of a sudden, that's no good. We want PyTorch. Everything is just changing so rapidly in that sphere. To introduce new systems into rail environments takes a very long time. To embed them into rail environments and other industries like that, to build dependency, to build trust, particularly from a safe environment, takes a lot of time and commitment. So what you've got there on the left-hand side is something called technology readiness levels. Don't know if anyone's come across that before. So it's a NASA-based idea on how to evolve products and embed products and realize the benefits over time. So effectively what you do is to start with, you take a proof of concept, you take an idea, you evolve that idea, you ideate that idea, and you then start to demonstrate it in your useful environment. And then you start to move that towards trialing that constrain that to a specific example or a specific region. You grow that over time, you embed that in over time, and then you can start to think about scaling, and then you scale that system, and you can start to build dependencies on systems. It tends to be that those systems will look to try to be embedded over 5 to 10 years, and then from the rail perspective, you need to build systems that will last for 25, 30 years. Yeah. Doesn't meet with the pace of AI as we stand. So you've got all these things and challenges working in that industry on how you build systems, apply them, and be in them for the long term. Most ideas around rail and AI only ever get to that lower TRL levels, so ones and twos. Lots of money is pumped in from places like UK government for ideas and evolving ideas, but to scale that and be in that for the long term is very difficult, and that's the challenge that we face at the moment. So Omnicom Balfour Beatty then, so I'll talk a little bit about the company that I work for, and a little bit about explain a bit about what we do. So we're effectively an SME within a big corporate. So Balfour Beatty is a massive construction company, UK based, but operates globally. That's £9 billion revenue a year, so it builds things like Olympic stadiums, bits of HS2, things like that. And it's existed for over 110 years. I don't know which one's Mr. Balfour and which one's Mr. Beatty on that, but no doubt it's one of them. So Omnicom Balfour Beatty, like I say, is a small little technology company within that big construction company. We started out as a startup in the 90s, based here in York. We've then grown, acquired a couple of other businesses, and probably about 6 or 7 years ago, we were acquired by Balfour Beatty, where the idea was to say there from Balfour Beatty that, big construction company, automation is coming, we need to adopt and start taking on technology. This is probably a better explanation of what we do as a business. So, in summary, we capture a lot of data. We locate and we process and extract decisions from that data. And it's all intended, we're trying to make rail infrastructure safer and more maintainable. So it kind of spans really across different methods of gathering data. So we'll gather large quantities of things like LiDAR data. So we will be able to determine where infrastructure is. Big problem in railways is knowing so much of it. Where is all that infrastructure? What is the age and the condition of it? And the ability to actually send people out to site and understand things about the infrastructure is becoming harder and harder. We're into remote condition monitoring, so we went into trying to add sensors to infrastructure, things like level crossings, so we can start to understand the health of that infrastructure and remotely start to diagnose and predict and prevent when those sort of things are going to fail. And we are into doing things with looking very closely and monitoring and measuring the infrastructure and its condition. So again, lots of gathering of large quantities of data, extracting decisions from that data, and trying to, again, predict and prevent when we were about to see any failures in the infrastructure. So the boring bit then, I guess, so that to understand how we go and solve some of the problems that we talk about, then this is rail infrastructure, and this is track, basically. So trains run on rails, and it's very important that those two rails stay equidistant apart so trains don't fall off rails. So the rails themselves fit to things called sleepers. So it's big bits of concrete that run between the two rails. And then they're fastened, the rails are fastened to those sleepers using something called a clip or a fastener. So effectively that holds that rail in place. And there is one sleeper approximately every meter, and then there'll be roughly about generally four fasteners around each sleeper. So that's a lot of infrastructure and fasteners that are needed to keep rails in place. So traditionally, the way things work on railways, and this has happened since the Victorian days, is people will check that infrastructure by going out with gangs of people and walking up and down the track and seeing that everything's in place that should be in place. Where it's not in place, what they will do is they'll take a pencil out and they would scroll that onto a report and then take that back to their maintenance depot and they would say, make a plan to go and fix it. And that happens traditionally every 2 weeks in general across 20,000 miles of UK infrastructure. The limitations and the difficulties there are finding people who want to do that. Yeah, it's surprising, really, isn't it? But in in the winter we've had, people will have to walk up and down in that wet weather, inspecting that track. And natural human instinct is try and do that as quickly as possible because you're getting wet. Limitation as well is the access times. There's a lot of demand. Customers want trains running all the time, and effectively that squeezes the access to be able to walk up and down that track more and more. So the limitation starts to become you can only do that in the middle of the night, and when it's in the middle of the night, pouring down with rain, all you want to do really is get from A to B. It's a challenging job. There's also the human element. There's that repetition, that boredom of walking up and down that track. It starts to bring in humans are fallible, and it becomes more and more difficult to maintain. We have in the UK probably a history in recent years of certain failures. So dating back to 2020, there's probably been 3 major accidents in the last few years. So I think 2007 was probably the most recent. Sorry, it's going to be 2020, it should be 2000. But 2020, let me get this right. 2000 was the Hatfield rail crash, which effectively a track defect was found in track, which managed to derail a train, multiple casualties. And then 2002, Potter's Bar, there was a points failure, again, derailed the train, and there were the fatalities. 2007, the most recent one really was at Grey Rig, where a set of points failed, and there one fatality, fortunately. That picture there is from that rail incident. The inspection and the following that kind of deemed that there were a number of failings found in the inspections of around that time, and there was an approach to try and change the way that we do track inspection in the UK. So track recording, so actual sending out trains to measure track, is not a new thing. So we've been doing that in the UK since the 1970s. Some of you might see them when you stood at station platforms, yellow trains whizzing past, and that tends to be fitted with all sorts of technology that do things like measure the condition of the rail itself or look at the overhead line. And we've probably been engaged with looking at image inspection since probably the early 2000s. In fact, when the Grey Rig incident happened, there was already video recording on there, but there's an article that was in the Evening Standard managed to highlight the limitations there, where human eyes would have to play through that image capture, and it would take a considerable amount of time for somebody to play through that and identify the faults that were in the rail. So in 2008, we started some work as Omnicom Balfour Beatty with Network Rail, looking at ways on how we could add automation into that inspection process. So over the years, what we've been looking at is how we can get the right outcomes to improve safety, improve the consistency of inspection, and also make it cost effective. So the journey probably from an AI perspective has started probably around about 2010 from our side. Now, initially, we would take these things through that TRL model. So we did a proof of concept, we did a trial around 2008, and then we started to scale the systems beyond that. And now we're in a position where we are inspecting 13,000 miles of track every 4 weeks. So there's probably quite a lot of railway speak and railway talk in there, but primarily what we're doing is we are fitting a load of technology to the underside of a train. We are capturing images very fast, and we are then extracting that information from those images. So we've got to this point now. There's 5 trains running around the UK capturing that 13,000 miles of data. The cameras. Something called a line scan camera. So what that means is it captures a line of pixels at a very fast rate. So it's something like 2,048 pixels wide, and it will trigger then based on distance. So it could be up to 200 miles high, yeah, at 0.8 mil resolution. Anyway, take a bit. So then when we've gathered all that data, our job really then is to apply elements of computer vision, which is now stretching into AI and deep learning, into making decisions from that data and identifying potential defects within the track. That's then passed for human verification. So whilst we are applying AI in this industrial sector, having that human in the loop is very critical for certain safety aspects of what we've got to do. So we're not quite there yet with the classifications of defects. What we're very good at doing is saying something is not right in that track. So there's all sorts of little things that we've got to try and identify because we've got to meet a certain standard, and the objective really is to do as good a job or better job than that person walking the track at a lot faster rate. So whereas a human could walk the track, a section of track that they would normally on a track patrol cover maybe 2 miles on a track patrol, we were able to cover 450 miles in one shift. So the benefits of that automation are there. It does create vast amounts of data though, and it creates a very big data problem in terms of how we move that data around, how we apply that automation, and how we're moving that through our image processing environments. So we acquire around about 25 terabytes a day to disk, and those disks currently will land anywhere in the UK. So we've got to be able to turn that data around very quickly with the help of DHL, maybe not Royal Mail, but we've got to shift that data around back to a processing center, churn through that very quickly, and present that for inspection. The process is very simple. We have a bunch of hardware on the trains, like I say, that records data. That data then we have to apply the automation on. So shifting that data around is a major factor. From that point, we create what we call a candidate. So that candidate is a candidate of a defect that has that human in the loop verification at that point. And then from that, we convert that into a report which goes on to a section maintainer. So it's a maintainer somewhere out in the country, and they will review that and work out how they're going to go and correct that track. There are a number of stress points, obviously. I mean, we've been operating this for a few years. Reliability of hardware, stress point number one. So introducing a system, the system's got to last for 10 years. We set out with it lasting for 5 years. The funding's not there. You've got to sweat that asset longer. It's got to last for 10 years. So it's a harsh environment under a train. I wouldn't want to be strapped there myself, and you need hardware technology that's not necessarily always suited to those environments to be able to operate in those harsh conditions. The volume of data is a massive problem, 25 terabytes a day. Okay, so each train's probably 5 terabytes of data. That's still a bit too much to be shoving up through the cloud. So being able to shift that amount of data through is a problem for us. Accuracy, obviously, from an accuracy perspective, that's what it's all about. What we're trying to get is very accurate decisions so we can operate the railway. So we've always got accuracy challenges. We always get queries. Did we find that right, or was that wrong? So challenging those and always driving accuracies is key. And performance. So how quickly can we get to the results? That's very, very challenging for us. We've got to churn through that data as fast as we can, and it's got to be out to that person in the field to fix the track very quickly. If we generate too many candidates, that's a problem, because you've only got a certain amount of people, humans in the loop. So controlling false positives in these systems is a real challenge. So you don't want to generate too much workload for those individuals and that small team. But what you also don't want to do is kind of create so many. So there's an ergonomic thing there as well about the repetition of pressing reject false positive, reject false positives, and sometimes you can miss something that way as well. Trust is the next thing. So in order for all these things to click, you need that trust from your end customer within the field that everything that you are doing is replicated with what they're seeing on site. So the big challenge in terms of the journey of getting there has been building that trust of a system over time and sustaining that trust in the system over time, because the people on the ground will know that track infrastructure better than us, and they've got to trust the system for the system to work. So in the early days of PLPR or of the system, then we applied very traditional techniques for image processing, and I'll class as machine vision in this slide. So that would use very off-the-shelf, commercially available software, and it would do things like segmentation, edge detection, and this is kind of very much a precursor to some of the deep learning type models that are applied today. The training of those models and how that's applied, very labor intensive, and then the trade-off really in terms of has been the performance constraints, plus the trade-off between accuracy and the reliability of the system versus the numbers that come through. So accepting a high amount of false positives to keep the accuracy has always been a fine-tuning piece of work, particularly in that safety environment. So deep learning there's been the revolution in this space really for the last few years. So we probably started that journey maybe about 5 years ago, where we started experimenting in this sphere, and our objectives really have been around reducing that workload aspect, improving the accuracy or retaining the accuracy, adding as much automation as possible, and trying to challenge the performance of the systems. The reason why in the last couple of years it's been viable is that the pace that AI has just evolved over the last 5 years is quite phenomenal. The availability of it has been great. Our domain knowledge within the industry, but also just within our organisation has grown over that 5 years as well. The dawn of new compute has made it more viable, and a more affordable compute has made it viable for us as a business. And we've been benefited from keen and collaborative customers who want to take these things to the next level. So where we are today, I think, is kind of, we've seen a shift from that machine vision segmentation approach. The massive improvements in terms of false positives. So we've reduced false positives by applying deep learning models to a factor of around about 90% in most cases. We've done that while sustaining the accuracy of detections. It's very important that we keep that accuracy level because it's the decisions in terms of the maintenance are made on that. And we've been able to improve on the performance of making those decisions as well. So being able to, we've moved away from having stacks and racks of compute to smaller scale compute that's able to churn through the same amount of data faster and more accurate. So probably the key factors in terms of that journey to success has been, a bit like Dimitar hinted earlier, very well structured, very well organized, labeled data. And that's where the year's efforts have gone, really, is creating that accurate labeled data set, understanding the ontology that we need to apply for those machine learning pots, and being able to understand and define that acceptance criteria early on. So, like Dimitar was saying about biases in data, our biases are more around skews in data. If we're hurtling around railway infrastructure every week in, week out, our skews are more likely to be in things like the weather conditions that we're capturing data on, the different vehicles that will move differently so that the fields of view will change. We've got to work in daylight, sunlight, rain, elements of snow. So they're our skews, and they're the things that we've got to try and build in there. The other ability we've got is, and I'll go a bit techie this one maybe, but because of the onset of the GPUs, etc., it allows us then to stop having to shift that data around the UK. So, unfortunate for the courier service, which probably gets a nice amount of revenue each year from shifting disks around. Where we can move to now is start to make those decisions on the fly. So shift away from the data centers, having to churn through the data. We were able to start to apply those decisions and that information on the edge, and we were able to start to generate that on the fly in almost real time as we gather. So that means that effectively we've now got systems that are able to keep up with that 125-mile-an-hour travel through the infrastructure, but also generate all the outputs needed at that same time. So just summarize really some of the key factors, I think, in terms of success of applying deep learning from our own perspectives within our own business. And I think there's probably three key driving factors to making it a success, really. And I think the first one is that structured data again. So we are blessed within my organization to having access to an unparalleled amount of data, effectively. And that data is very boring, yeah? It's a bunch of rails, it's a bunch of fasteners, a bunch of sleepers. It doesn't change much. So it's nicely organized and nicely structured to allow us to make certain decisions on them. Yeah, we don't have the variability of rapidly changing scenes and things like that. So it's primed, that data, to be able to apply deep learning and AI on. So we also have industry domain knowledge. So we understand railways. We've worked with them for the last 20 years. We understand how they fail. We understand the failure modes of a fastener and a sleeper and a piece of rail. We could bore you to death on those, but there are all sorts of conditions and reasons why they might fail. And because of that 20 years experience and the teams of people that we work with, we were able to understand that domain area well. And then if you mix that in then with the technical expertise, so people who are working in computer vision day in, day out, maturing themselves with the latest technology, that mix of data, industry, domain knowledge, and technical expertise is the formula that you need for success. And that's kind of why that's worked for us, I suppose. So I'll summarize really in terms of like the key learnings. So in terms of making things a success, I think number one, my key learning will be it takes time in industry. So I think again that TRL level, there is a lot of money floating around in industry at the moment. If you tag the word AI into a proposal, people will question why it's not in your proposal right now. I would say all the access to all the funds and the grants, etc., are all being dished out to things that say AI in the proposals, and they will take you through that proof of concept area. But to sustain that, and to sustain that for the next 10, 20 years, you've really got to be able to demonstrate your proof of concept, scale that, and be able to operate it for the longer term. So I think endurance is a big thing about making those things happen. So being committed to earn that trust of your customer, be able to be with them and partner with them for the longer term is critical to that success. But also embed yourself in their business problem. I mean, it's. I think I was on a certain call the other week, and somebody said quite refreshingly, it's not just about the tech. The tech's there and the tech's ready, but what people need, or what the customer needs, is the tech plus the ability to realize that business value by taking you on that journey and changing things and interpreting that into the business value. So AI is not the only thing. Think about the tech, think about the business benefits. It's got to be commercially viable. So for an organization like mine, and I would imagine every organization, there's got to be profit in there. It's got to be commercially viable and stack up, particularly to be in there in the long term. And the final thing would be luck and timing. I think you've got to be in the right place at the right time with the right partners at the right time to be able to take systems and be able to scale them. That's it. Thank you.
So that leads us to the Q&A. Are there any questions? I've written down one already from online. That will be for you, so you might need your mic again. Are there any in the room before we dip into the online questions? I know you guys are getting cold, so I'm going to make sure that we get through this. Yes? I'm going to pass.
That was great, and thank you both. That was really interesting about the bias and how that could be dangerous. But coming back to the rail inspections, I can see that could be useful. But you say it's about business value and benefit. Have you measured how that has improved rail services, particularly in the north of England? Because there's been a lot of criticism of rail services in the UK, so presumably it has improved.
Should we take on this one again? So I think, I mean, railways at the moment are really struggling with funding. And I think if you look at the news at the moment, you will see it's still a very heavily unionised industry as well. And there are a lot of cost cuts across railway. I mean, I think it works in a thing called control periods, where the government allocate a set of funds for every 5 years. So measuring the value is this tricky thing, because it's like there are a lot of intangible benefits from the data. There was a report that I did see where what we've it kind of concluded from the system delivery that when you look at it statistically, faults still occur in rail. Yeah. What we've started to do though is see a reduction in the amount of critical faults in rail, because the consistency of reporting has increased. Whilst you've taken what we've managed to do is take away the people walking out on the track to find faults, and what we've changed is the mentality towards being able to focus people who go on the track to fix faults. So what you've seen is a more consistent track inspection, but also the focus of that resource on fixing faults before they become significant faults. That makes sense?
Are there any more questions? Okay.
Thanks. Very interesting. Related to the question that was asked by the gentleman there, I believe there is a continuum between beginners of faults which may not need assistance and very critical ones that need assistance, and there's also a capacity of engineers repairing. So is there a lot of redundant analysis that you do, kind of rediscovering faults that have not been looked after, or what's the whole workflow?
Yeah, I mean, the way the system's designed and the way it's implemented is designed to take each inspection as an independent inspection. It's interesting though, because it occurs every 4 weeks, you can start to drag out trends. So I think one of the next big things is around change detection in the infrastructure. It's always been a constraint with the volumes of data to be able to do that, but now it's starting to become more viable to look at that change in that infrastructure condition over time. And you can start to drag out and predict certain things based on the scale of change. Something like a broken rail, though, will occur in an instant, in the matter of hours, depending on the condition of it. So it won't work in all cases, but I think I think change detection is probably the next big thing.
Yeah, just put myself in the shoes of the AI. Say, come on, I told you 10 times there's a fault there. Stop. Do something about it.
And then I think that there are other shifts. We spoke very much about the vision side there, but there are other track measurement systems that are lower cost, less data hungry, that can be mounted to things like passenger vehicles, where you can start to drag out certain trends from a lot more frequently, because a passenger vehicle will go A to B day in, day out. The volumes of that data to this day have always been a challenge, because it's too much data to serve to an engineer. But with AI and with other things that you could fuse that data with, you can start to automate those decisions and start to extract that intelligence a bit more dynamically and present the results or the outcomes to your end users. Yeah.
We have one more question. It's from online, and then we're going to wrap this up because I'm aware of the time.
Okay, so someone online has said there are a lot of tangible benefits to using AI, and Omnicom has had the vision to get on board very early on. What would you say to other companies not yet engaged with incorporating AI in their activities?
What would I say to other companies? There's a fear factor, I think, of not embedding AI into your organisation at the moment, I think. Working with a wider construction company, I see all the time that we're always looking at ways of embedding AI at the moment, out of fear as much as anything else of being left behind. It won't work for everything, I don't think. We had a decent play around with large language models earlier in the year, but I'm certain there are probably some commercial benefits there. But initially we found more productivity benefits internally. So I think at the moment, I think that it's driven by the general fear of being left behind. But only certain companies will be able to adopt that into a commercial model, I think.
Thank you again. Applause to everyone. Just quickly, a final wrap up, so it will only take 2 or 3 minutes. Just give me your time. I just quickly want to highlight the upcoming events, because I keep getting emails about this. So this event series is not just coming from one school. So today we had, luckily, computer science, but also Institute of Safe Autonomy, and obviously we had an additional guest speaker from the industry. The event in February will be run by York Law School and Department of Sociology. Then we are lucky enough that in March we have School of Arts and Creative Technology, and they might be working together with CoStar Live Lab. And then for the final event, which will be a panel discussion, we're going to be running it as a School for Business and Society and a potential other partner. There is not more detail on these at the moment because we don't have more detail yet. As soon as that's out, I will share it with everyone who's interested. To get the information from us, you can either engage with us online on LinkedIn, or again, a reminder, if you do want to have further information, that's what the QR code is for. So everyone who signs up for the survey which is behind the QR code, will keep you informed. I just don't want to spam people. That's why I kind of say, if you're interested, let us know. If not, that's absolutely fine. It's your choice. No one is forced to do this. Finally, just quickly, as part of the speaker series, we kind of want to highlight our amazing academic members of staff who are kind of doing research, especially in computer science, for years already in this industry. You have obviously on the lovely guest speaker Dimitar in the middle there. But if anyone is interested to reach out to any of the academics who have been working in this area, on the next slide we have a few more information, please just do. There are also other initiatives which might be quite interesting for students or businesses alike. There is plenty and ample opportunity to kind of get engaged with the school and the university in per se. As I said, these will be recorded, so you can see the slides in a more slow pace in your own time. I just want to wrap this up by saying a big thank you. Obviously, first of all, to our speakers, Dimitar and Stephen, but also to John, who's going to come back in a second. He was the kind man who kind of guided everyone upstairs and downstairs. He definitely got his steps in today. He offered us the venue. Then Grace and Vicky, who are absolute super women who have helped me behind the scenes to organize this. Bo Dirty, and obviously Caroline, who gave us some money, because we need money for these. Eagle Lab, who have been sponsoring the cake, so please make sure you eat some on your way out. And obviously Craig, who has been with us the whole time to kind of make sure that you have a nice recording afterwards and people online can join us in a decent manner. All the pictures on here are from Pixabay, and also thank you to all of you guys for actually turning up. I know it's been a fridge experience today, so please make sure you get warm again after the event. Everyone online, thank you for joining us. It's nice to kind of spread the news a bit. And other than that, I wish everyone a nice winter period. Just relax, have a good time, and maybe join us for a bit of conversation. Everyone online, thank you for joining us, and have a lovely day, night, wherever you are. And that's it. You can relax. Go your way. Thank you, guys.